Single crystal means, by single crystal we mean that only one phase is present. One phase is present with one grain size. If we talk about polycrystalline material, let's say this is my material and it is divided into various compartment which has different grain size. The phase is same, but how the particles are arranged in this grain size are different. So, this is grain size 1, grain size 1, this is grain size 2. Okay, if I have a single crystal, then this has only one grain size. By one grain size, it means that I'm magnifying this image here, that this distance different here, this distance is different over here. From wherever we go, if we measure from here even, from every point to other point, the distances are different. So the directions, in whatever direction, if we measure the physical properties, is different. In case of single crystal, physical properties, which I can say electrical property. Is it conducting? How much conducting? How much is the resistance? Like these type of questions. Okay, so in the single crystal, all the physical properties are different across all the directions. So our answer is true. So our answer is true. Right? Next question. Average property of large particle is same as property of the one of the grain size. Suppose this is my material. It has different grain size. See. Are you following, students? So if I measure, let's say, electrical property of all this grain size 1, 2, 3, 4, I will have some values. Say suppose I have around 4, 5 Simon per centimeter. Simon per centimeter conductivity. But the question is, does this grain size, the grain size number 1, has the same conductivity? Is it yes or no? Is it a yes or no, students? You can answer in the chat box. If will be the physical property of grain size number 1 will be same as the average property of all the grain size, all the grains. I mean, no, because this might have 5 Simon per centimeter. This may have 2, but the average will come out to be 3.45 Simon per centimeter. So it is false, because the nature of the material has different. This grain size behave as a single crystal, but this whole material is polycrystalline. Okay. Next question. Next question. How domain size is related to the magnetic property of the material? This question, this topic was discussed in the week 2, lecture number 4. Hopefully you have seen the lectures. Will you be able to answer how domain size is related to the magnetic property of the material? Priyadarshini, would you like to answer? Are you able to see my screen? How domain size is related to the magnetic property of the material? So let me explain. It is we have a bulk material, macroscopic I mean. Thus magnetic moments have enough space to arrange itself. Suppose it is conducting, sorry, it is magnetic. So the magnetic moments are arranged like this in a big space. Like big space means in a bulk material. When we reduce the size to the nanoscale, this there is not enough space to arrange them parallel to each other. So they orient themselves differently to occupy in that minimum space randomly. So now the material which was earlier in bulk was magnetic is no more magnetic in the nanoscale. So in this domain, as the domain size has been decreased, the overall magnetic property has been affected. So this answers our third question as well. Next question. Heat and lubrication relation to the small scale. How the nanomaterials are applied when we use lubricants which are used in engines. How the lubricant of the smaller size affect the car engines. This was also discussed in week 2, lecture number 4. Okay, the lubrication property of the nanomaterial can works both ways. So I will explain you over here. Since I do not have enough space, so I will move on to the next slide and cover that in this part. Nanomaterials loses and gain heat very fast. Okay. Because since the thermal mass is small, a bigger block will take more time to lose and gain heat because of its mass, because of its size, but a smaller block of nano size will take lesser time, right? So when the lubricant particles are small, then they can why do we use lubricant? for the good movement and to avoid the heat dissipation. So since they lose and gain heat very fast, so we can use in the car engines easily. Right. So this answers our 4 questions of week 2, lecture 4. Do you have any doubt in this? No problem. Next question. First, we will understand how these nanomaterials, how we study the surface of these nanomaterials. There are a lot of other characterization techniques that we use to study the features, how they look, how the phase has been formed, has the phase which has been formed is pure or not, how much impurity is there. So we use various characterization technique. We use XRD to know about phase. We use, I have discussed this feature in previous class, scanning electron microscopy to see morphology of nanoparticles. How do they look? Okay. But to study the surface, we use AFM. AFM stands for atomic force AFM stands for atomic force microscopy. This is a part of SPM, scanning probe microscope. There are few students who have joined recently, so I hope you are following. If you have any doubt, you can raise your hands and ask me the questions. Have you all studied about AFM in the lecture? You can write your response in the chat box as well. Rishabh, do you have anything to say? Do you have any doubt regarding this? Okay. So AFM is used to study the surface. We will see how does it work. This is, as we can see in the image, this is a surface atoms. It has a tip. This is a cantilever to which the tip is attached, and this cantilever has piezoelectric nature. What does piezoelectric nature mean? Piezoelectric nature means that it will change its behavior according to the current response. Okay. This laser hits the cantilever. Cantilever moves its position depending upon the surface it's glide over. The surface is conducting in nature. it can conduct electricity because we have electrons on the surface, right? So this tip, so this cantilever, the tip is also conducting. The tip moves, the cantilever moves itself, and the response is recorded by a photodiode. The photodiode is attached to a computer which gives a feedback. First it has given XY control, and the feedback which we get, it get Z control. And this response is recorded. AFM can work in three different type of mode: contact mode, non-contact mode, and tapping mode. I will go briefly over this. As the name suggests, contact mode means the tip. If this we have a surface, like this is a rough surface somehow, like if this is a surface like over this. This is a tip and this is a cantilever. The tip is touching and gliding over the atoms by remaining in the contact. Okay. Tapping mode. In tapping mode, if we have this surface, it touches the surface regularly. It does not glide, it touches the surface. Like this is a tip. Once it is here, one tap, second tap might be here. Okay, there's a frequent disconnection between the surface and the tip, but here there is no disconnection. Non-contact mode. This is tapping mode. This is contact mode. This is non-contact mode. Non-contact mode, what happens is a very interesting phenomena. We have this surface, and the tip does not touches or tap. Then how does it record the surface behavior? In a nanoscale, a interesting phenomena happens, which is called tunneling of the electron. The surface atoms, since the surface is conducting, if the gap between the tip and the surface is very small, then electron does not need a medium to travel. Electron does not need a medium to travel. It travels itself through the air. Okay. Here we need some connections in these two cases, but here there is no connection. If the gap is very small and very nano small, like around 5 to 6 maximum nanometer, the electron can itself tunnel, and the tunneling happens constantly, and the surface features are recorded. So this explains our non-contact mode. Here you see a diagram over here which gives how the distance d and the current is changes. Can you tell me, is it directly proportional or inversely proportional? What kind of relation does it give to us? You can write your response. You can write your response in the chat box. The figure which you're seeing is directly proportional or inversely proportional. It is inversely proportional. See, as the distance is small over here, smaller distance, the current response is high. Here the distance is larger, the current response is smaller. And this is the equation by it relates I e to the power, there is some constant, negative signs because it is inversely proportional, and exponentially, like it is inversely proportional exponentially, I mean to say. This is the work function depending upon the distance. Phi is the work function, energy barrier. E is the electron charge. M is the electron mass. And the constant which we use over is Planck constant. V is the applied voltage. We have to apply some voltage. It can be 5 millivolt, it can be 10 millivolt depending upon the surface we have. And D is the tip and sample distance. Alright. We have to take care some of the properties of the tip. Cantilever should have a sharp tip. Okay. There should not be fat tip effect. The stiffness of the cantilever needs to be less the effective spring constant holding atom together. Okay. The spring constant should not be as very much stiff because it cannot then give the good surface features, since it will not be as smooth contact with the surface. The tip will not be in the smooth contact with the surface. Fine. The tip should have a radius of curvature less than 20 to 50 nanometer. The radius, if this is our tip, so it should be around 20 to 50 nanometer, and this is a cone angle. It should form 10 to 20 degrees. One more, let me explain. You can answer this question. Which tip is better? This has a smaller angle, suppose around 20, and this has more, say it is around 75 degree. So which tip should be used for AFM? Tip number 1 or tip number 2? Any answers? Priyadarshini, would you like to answer? Am I audible to you?
Yes, ma'am.
Okay. So would you like to answer? Which tip is
Yeah.
good for the AFM? Tip number 1 or tip number 2?
Number one, ma'am.
Why?
Ma'am, I am very new to this subject, ma'am, so I'm unable to
Okay, no
understand,
problem.
ma'am.
Here we can apply the fact that this is our surface. It has atoms, right? Which form these little gaps, these little valleys. So the tip which is broader will able to give you the right, will able to give these information between the valleys, or will a sharper tip which can fit into these valleys will able to give the features right? Are you following me?
Yes, ma'am. Yes, ma'am.
So can you tell me now why tip number 1 is a better tip for AFM? Did you follow over here? These
Yes, ma'am.
valleys are formed. So these valleys are very small. So tip which has a smaller cone will able to give these surface features, will able to give better contact mode, better will able to glide over the atoms. A,
Yes,
a fatter tip will leave these some surface, right?
yes,
So
ma'am.
that is the reason that we should not go the cone angle beyond 10, and minimum should be 10,
Yes, ma'am.
right?
Yes, ma'am.
And one more thing is that okay, next thing which we need to take care about the tip is that the tip is very sensitive. So the surface should not be much hard, like so should not be much rough surface. Roughness should not be high. No surface is smooth. On the macroscopic level, you may find the surfaces are smooth, but no. And at the nano level, when you see these things under microscope, these are rough. And high roughness will lead to the breaking of the tip. So, and these tips are very costly. So we have to take care that we should not run the samples which have high roughness.
Yes, ma'am.
Next question related to AFM. Can you, these pictures which you are seeing, this picture A and picture B, we need to understand when we have to perform the contact mode, when we have to perform the tapping mode. Okay, the tapping mode is performed when we are studying the conducting features of the sample. The samples are prepared. I will explain you the sample preparation also. Let me write sample preparation. These are the features which we see. These all images belong to one sample only, but just by changing the modes we are getting different images, we are getting different information. Like here in tapping mode we can clearly see how large and small particles are there. We can differentiate between the high roughness and low roughness. Suppose here we have the scale of 200 nanometer. This white part means the particles are of around 100 to 200 nanometer. So these particles are of around 200 nanometers. Whereas if we see this particle which belong to this shade over here, so it means it is around 80 nanometer. This is a bar chart which we get when we perform AFM, and then according to the scale we understand that what kind of, like, what is the distribution of the sizes of our nanomaterials. And these varied distribution, like some particles are of very smaller size, some particles are of very like more over than 100 nanometer. So these distribution creates roughness, and we are able to study. Whereas this features is not clearly visible in contact mode. The roughness features is not, the particle size are not very clear in contact mode. So what do we learn from here? That if we want to see how the distribution of particles are there in the nano level, then we should perform the tapping mode.
Yes, ma'am.
Next question. Next question. Here you can see another AFM images which we have. On these AFM, first what we do, we study roughness. The we study roughness,
Size.
yeah, roughness, that is related to morphology, size. After when we get these images, then we move on to the other study which we perform according to our like requirement. On the AFM we can perform conducting, how much sample is conducting, what is the potential, like all, not all surface, if our surface is positively charged, if our surface is negatively charged, that type of study can also happen on AFM. Potential, electrode potential, like surface potential, electrical potential. We can perform resistance. Okay, suppose here, as you can see, this bar chart, 5 millivolt. This is a 5 millivolt. The red region has lower potential, electrical potential. This region has higher. There was some study was going on. We increase the potential, and there was some changes. These changes are not reflected on the roughness studies. You cannot see the changes clearly when till M. In Q part you can see there is some gaps. There are some valleys and cavities have been performed, because see it is so deep. It is around 0 to around 2 nanometers. To clearly see, we have performed electrical potential AFM. Then it is called EFM. EAFM. Here it was there, but it was not clearly visible. But as we proceeded, it became much more visible. So this is a bar chart. We can differentiate between what potential is there at what surface. Okay. Now we will move on to the summary and questions related to the lecture 5, week 2. Anyone has any doubt till here?
No, ma'am.
Okay. What is thermodynamics? What is thermodynamic if we want to study the thermodynamics of nanomaterial? Thermodynamic is the study of heat, like
With,
energy, heat.
with the physical parameters of
Yeah, yeah.
system and surroundings.
Physical parameters and
Of system and surroundings.
yes. What do you mean by physical parameters? We are studying heat with which kind of parameters?
Temperature,
Right.
humidity, like this, ma'am. Heat. And
Heat is there.
yeah.
Yeah. What
Moist.
physical?
Mm, water. Physical
Yeah.
parameters.
Are you saying water?
Yes, ma'am.
Um, Physical parameters mean what properties like pressure
Ah,
we can
for sure.
study. We can
Yes,
study
ma'am.
how the heat energy is varying when
Mm,
we increase or decrease the pressure.
mm.
Like in beaches, we have high pressure current, low pressure current, right?
Yes, ma'am.
Because the heat over the ocean is very warm, so the density differs. So that kind of parameter, physical parameter means pressure,
Okay.
temperature, density. So these changes the values of the heat which we get. So thermodynamic is that study. System and surroundings. What is a system and what is a surrounding?
What kind of method we are following is known as system?
Are you asking a question or telling me the
No, ma'am,
answer?
I'm telling you the answer, ma'am.
Okay. What is a system in a thermodynamic when we say,
What type of method we are following, methodology?
for example, like which methodology you're
No,
talking?
no, ma'am. Some people will use heat that extract and all for doing extracting nanoparticles. Some may use at room temperature. They will synthesize the nanoparticles likewise, ma'am. I'm
Okay,
telling you. I don't know
I
how
get
far
you.
it is correct.
No problem. We are here to discuss these doubts only. No problem. So what are you telling that some people make nanomaterials using some temperature, some can make even at room temperature.
Yes, ma'am.
So this approach, how the nanomaterials are made, are formed, is fall under the synthesis approach.
Green synthesis, likewise,
Okay,
ma'am. Green synthesis.
you are classifying the nanomaterial on the basis of synthesis approach.
Mm.
But here, our aim is to study how nanomaterials behave under thermodynamic conditions.
Uh,
So, what is a system? We are saying study of heat. So, what are we studying? Are we studying a glass? Are we studying a box? Are we studying a beaker? So, the focus what we are studying, the material which are studying is the system. This is a language of the thermodynamics. Okay, this is a language in which we define some things in the thermodynamic chemistry. So the system which we are focusing is a system, and everything surrounds that. Whatever is there is our surrounding. Suppose we have a closed system and there is some random gas is there, like suppose oxygen, and here we have carbon. We want to study the the internal energy of this box. So we are not, if this is a closed system, we do not care about which gas is there, even if gas is there or not. We are not worried about surrounding. Our focus on is in this box. So this box is called our system. So this is a language of thermodynamics. Are you getting?
yes, ma'am.
Yeah.
Yes, ma'am.
Type of systems. Next question. Type of systems.
Ma'am, surroundings, ma'am.
Surrounding, everything apart from the system is surrounding, and everything apart from the
Exam-
system.
Example.
Example, like we want to study how much pressure is there in your, like if you're cooking food, a pressure cooker, we want to study what is how much heat is there. Pressure cooker is closed, right? So our focus, our system, if you want to study pressure cooker, then our pressure cooker is a system,
Mm.
and everything apart from the pressure cooker, like your gas, your glasses, everything is surroundings. That is okay.
Yes, yes, ma'am.
To
Yes, ma'am.
differentiate what we are studying, we have introduced the word system. Okay,
Yes,
are
ma'am.
you following?
Yes, ma'am.
Yeah. Type of systems. There are basically three type of system. If we talk Okay, there are basically three type of systems: closed, open, isolated. If we are talking about in terms of matter and energy, just by looking at the names, can you tell me that in which system the matter is interacting with the matter of the system is interacting with the surrounding? Is it in a closed system, open system, or isolated system? I know you do not know about this, but just,
Open system, ma'am.
yeah, right. So in the open system, both matter, like matter means whatever you have in your system. If there are gaseous particle, if there are any solid particles, if there are any liquid particles, which can which can move in and out from your system to the surrounding, is an open system. And if it has heat energy, like if it has some like the if it has some warm gas, like warm gas, the gas can move from higher to lower region, na? Like from
Yes,
high
ma'am.
concentration to low concentration. So even energy can move in and out. So in an open system, both matter and energy can exchange in the surroundings. Okay.
Yes, ma'am.
In closed system, no matter, no matter and no energy is exchanged since it is closed.
Nothing can enter like that.
Yeah, nothing can enter. But in the isolated system,
Um,
matter does not
Specifically, we are allowing something or exiting something.
yeah, but in an isolated system, ma- energy can exchange but not matter. We have different if you want to study different type of conditions, then these systems are introduced. These every like closed system has different thermodynamic equation to study, open system has different thermodynamic equations to study, and similarly isolated atom. So that is why there was a need to classify these. Okay,
Yes, ma'am.
so these matter and energy are exchanging. So there are some processes going on. It is a kind of process in and going out. This process can be classified. Is it a reversible process or an irreversible
Yes,
process? Can matter come back to the system from the surrounding? If it does, even if the energy can come back, then it
it
is
is
a reverse.
reversible.
It is reversible.
Yes, ma'am.
And if it does not, then it is an irreversible process.
Irreversible. Yes,
Fine.
yes, ma'am.
So any like not just focusing on the like system and surrounding, can you give an example of reversible process around you? What happens? What is a reversible process?
When
Like you can
we
apply some
breathe in air,
conditions.
ma'am,
Sorry.
when we breathe in air, no, it is a reversible
What?
process.
Please
When
repeat.
we take in oxygen, no, it is a
Okay.
reversible process.
Yeah, it is a reversible process.
When we pull out carbon dioxide, it may be
When
irreversible
we
process.
when we
Pull out carbon dioxide, exhale carbon dioxide,
yeah,
it is a irreversible
movement of
process.
gases in your body is a reversible process. Are chemical process reversible or irreversible?
Chemical process, ma'am, it is irreversible, ma'am.
Yeah, but they are reversible under the condition which we are performing, right? That
Yes,
that depends upon the energy and which will be studied in the next slides. Okay, so
yes, ma'am.
melting of ice is a reversible process. If we give some its cold conditions, then we can get back our ice, and if we keep it out, we can get the liquid form. So it is a reversible process. Formation of curd is a irreversible process. whatever you do to that curd, it will not come back to in a milk form. Fine. If we give sour conditions to the milk, it will form curd. But if we cannot remove other sour conditions like bacteria which has been there in the curd and make it back to a milk, so that is a irreversible process. So these are a few examples.
Yes, ma'am.
Next question. Difference between thermodynamics and kinetics. What is thermo? I have explained you what is thermodynamics. It is the study of
It is
heat.
related to heat, ma'am. Using the
Kinetics?
heat. Oh, no, no. Kinetic is related to energy, movement of
Yeah,
energy,
yeah. Speed. It is related to
movement
the
of speed. Answer, movement
yeah.
of speed,
It is related to the speed, and
speed,
if we use a better word, it is related to rate
rate.
with respect
Okay.
to time. If we talk about,
Mm.
so kinetics is happens with respect to time, and thermodynamic happens respect to
To
heat.
heat,
So I have example of two, H2O and
coal,
coal. Um, we know if I have hydrogen gas and if I have oxygen gas, like if I have two cylinders, and if I mix those gas, will I get water?
hydrogen. One more is
Hydrogen, I have a hydrogen gas, I have oxygen gas,
mm,
and I just mix them in another beaker or cylinder. Will I
mm,
get water?
no, ma'am.
Why?
Um,
Like water is made of hydrogen and oxygen. Then why can't?
uh, the heat is processed there, ma'am.
We need to.
Heat,
It needs some energy.
yes, ma'am.
You said we need to give some heat,
Mm,
some condition. So there is a barrier
mm,
between from going to this process to this process.
yes,
So
ma'am.
that barrier,
Mm,
if it is high, then we need to give more energy.
mm,
If that barrier is less,
mm,
then we need to give less energy. So this
yes, ma'am.
lowering or increasing of the energy barrier,
Depending upon the barrier size, ma'am.
yeah, gives the kinetics of the reaction. Okay,
Yes,
even
ma'am.
if even if the the thermodynamic energy is low, like we need only some 2 joule or 2 kilojoule energy. Kilo is very high. If I need just 2 joule of energy, then it still need to pass through that barrier. And how fast and how fast or how slow will go will depend upon the barrier size. Si- Similarly, coal. We have coal. We have oxygen in the air. Do combustion reaction happens all the time whenever coal and oxygen sorry, are lying nearby. If coal is lying in an open space and oxygen is there in our air, will if will it spontaneously give the CO2 or carbon monoxide? Like we
No, ma'am.
usually have
When it
smoke.
burnt, only it will give uh, carbon dioxide
Yeah. So it is all about energy.
energy.
Fine. So this is the difference between the thermodynamics and kinetics. I will give further more example how the thermodynamics and kinetics goes simultaneously. Suppose I have a reaction A and B. This is a sign of reversible reaction. Okay, so wait, I'm making this arrow a bit longer and this arrow a bit small, and see, A to B can go spontaneously. Like diamond can change into graphite if you keep the diamond in an open environment, like in these room temperature and pressure conditions. You no need to provide any heat. But does it happen? If anyone has a diamond ring, does it change into graphite?
No, ma'am.
There's no need to provide energy. Even the room temperature energy is enough. But does it changes into graphite? No, it doesn't. It does not, because the rate of reaction is very slow. It is very very slow. It takes years, like years to years, to change. So that change is not even visible, noticeable. Fine. So this tells about the kinetics of the reaction. Both diamond is carbon, graphite is carbon, but still the rate of reaction is different. And why diamond is changing into graphite? Why it is not graphite is changing into carbon?
Because it is a irreversible process, ma'am.
Graphite to diamond happens under high pressure condition. Okay, it is a like it is not irreversible. It is slow, and then it seems irreversible, right? If we put graphite into high pressure condition, then it can change into diamond. But my question was, why diamond is changing into graphite? If we focus on this part,
Uh, because of the kinetic energy, ma'am.
kinetic energy is very slow. It is like kinetic
Yes.
is just playing how fast and how slow will go. But why it is changing, that kinetics does not answer.
Mm.
We get answer in our thermodynamic property.
Yes,
The
ma'am.
diamond structure is very stressed.
Mm.
You know, four
We have to
carbon bond
break
with
it up
tetrahedral
through heating.
structure. In the lecture, if you see, lecture number, I think 6, I think 5, lecture number 5 or 4, you have seen an example, an elephant, smaller elephant and a bigger
Yes, ma'am.
elephant. Yeah.
Yes,
So
ma'am.
in the smaller elephant has a lot of stresses.
Mm.
Hence, it does not perform well.
Mm.
Okay. It want to go in its bigger space. It want to loses out its stress. Similarly, there are stress in this diamond structure also. That is, it want to go in a more flexible structure, that is graphite. Graphite is very flexible, right?
It is very hard, no graphite.
Like it seems hard, but it is, we can break, like brittle. You can Graphite is used as a
In
lubricant
pencil
also.
lead.
Fine. In
Yes,
that,
ma'am.
in the pencil form, you find it hard, but it's smooth, na? That is why you are able to write on the paper. You cannot write with diamond on the paper. You can only write with the graphite because it's smooth. So it is more flexible structure than diamond. That is why it is changing into diamond to graphite, not graphite to diamond, even at room temperature. Next question. Now we'll talk about extensive and intensive properties. Before that, delta H. Do you know what is delta H?
Ma'am. No,
Delta
ma'am.
H means
Delta means heating, no, ma'am.
change.
Change.
If we are going from one process to another process, then One process require H1 energy, another process require H2 energy. And how much change we require is called delta H, energy change. Change in the energy. Okay, that is called. But it is an extensive property or an intensive property? Do you understand what is extensive and intensive property?
Yes, ma'am.
Okay. Yeah, what is an extensive property?
Ma'am, what did you say, ma'am, for delta H? The amount of
Delta H means that if I have a reaction H1, like A to B has H1 energy and C has H2 energy. The difference between C and AB will give you delta H. Okay. So my question is delta H is an extensive or an intensive property? Anyone? You can write your answer in the chat box if you want to. Delta H is an extensive property. What is extensive property? Let me explain you in this. I will come back to the other questions. Extensive property means there is a linear dependence on the amount of matter. Suppose I have like 1 kilogram of ice, so I need to convert into its liquid form. This will require which will require large energy? 2 kilogram ice to water, A or B? Which will require more energy, A or B? Of course B, because here amount is more. So the properties which depend upon the amount of the matter, linear dependence, those properties are called extensive properties, like internal energy. Every matter has its own energy. You have your own energy. That is called U. H, which we are talking about, enthalpy. Another thermodynamic parameter, A, Helmholtz free energy. G, Gibbs free energy. There is one interesting property about this Gibbs free energy, which I will explain you here. And lot of entropy, randomness. If I have a box of 100 gaseous particle, and if I have a box of 1000, like similar size of box, 1000 gaseous particles, which will has more chaos inside that box? 1000. So more randomness, more chaos is there. So that is entropy, basically in layman's language. Entropy. What is it next? Intensive property. Intensive properties are the properties that do not rely on how much matter is there and independent of the size. Coming back to the same question. Intensive property. Intensive property does not depend upon how much matter is there, and is independent of size. Okay. For example, density. Density, it is gram per centimeter cube. It is independent. If you have water in a bag, if you have water in a beaker, the density remains same of the water prior to the condition that the temperature is same, pressure is same. So density will remain same. Pressure, if you have a room, the pressure of the air is same all over the room. Be it on a corner, be it in the middle of the room, be it in the top of the like the roof of the room. The pressure is remain same. The unit of the pressure is Newton per meter square. Temperature. Temperature of a room all over the room remains same. There is, if it is 25 degrees Celsius, then it is 25 degrees Celsius. So temperature, density, pressure is an intensive property. Fine. So we have studied this much. So coming back to our previous question, is intensive property size dependent? Yes or no? Right. It is not size dependent. What happens if it is size dependent? What happens to the how the world changes, how your surrounding changes if it is size dependent? What happens? Then it will be a total chaos. If you want if ocean water, if the density becomes size dependent, then there will be a ship which in the same ocean water is floating, and another ship in the same ocean water is sinking, because now it has become size dependent. Fine. So it will be a total chaos if our intensive property becomes size dependent. So it is better that it is better for us that it is independent of the size. Example of extensive property. Though I have mentioned you, you can give your examples. Like if you have any examples of extensive properties. Gravity is an extensive property. What is the unit of gravity? It is. But on Earth it is almost same everywhere. So it is an intensive property. Intensive property remains same everywhere. Extensive property does not. Okay, what happens to my screen? So let me rub all these. I have other things to discuss. Okay. Next question. So one of the example of the extensive property is number of moles, molarity. So molarity is an intensive property, but number of moles is an extensive property. Okay. Next question. Delta H is a state function. What is a state function? We have discussed extensive property, intensive property. Then what is a state function? Is state function, if you know, is path dependent or path independent? You know delta H is an extensive property. So if you think of a reaction in terms of how it goes through, does it become path dependent or independent? Think of a reaction. uh, if you want, if you want um, an ice to be changed into gas, if it goes directly or if it go from ice to water to gas, will this energy change will be path dependent or independent? Think in this matter, and then you will understand delta is a state function or not. State function is path independent. I have told you this. Now tell me, is delta H is path depend is a state function or not? You know what is state function? Now tell me, delta is a state function or not? Consider this example, ice to gas. It is ultimately changing into gas. It requires here it has suppose 24 joule energy. It has I have to give energy, so it is suppose 50 joule per mole per mole. And if I want to go through this, it has 24. It has remaining 25, like 26. It is ultimately changed into gas. Energy requirement remains same. So delta H is a state function. It does not depend upon how the reaction proceed. It depends upon its final and initial states. Okay. So yes, it is a state function. Uh, the work which we do, like irreversible work or reversible work, which of them is a state function? Reversible work is a state function. because it does not dependent upon the path. Whatever path it goes through, does it is go slow or does it go fast, it will come back to its initial position. Irreversible work is not a state function. Okay. Next question. Yes, so I was about to tell you one interesting fact about the scientist who discovered the term gift-free energy. His name is Josiah Walter, oh sorry, Willard Gibbs. And it was the first, he was the first American to get PhD in engineering. And that he took in 1863. Okay. That he took in 1863. So that is an interesting fact about the the person who discovered gift-free energy. Now, moving on to the next part. Like I just wrote for your information, Willard PhD in engineering 1863. Now questions on energy barrier diagram. Hopefully you understand this diagram. If not, I'm explaining over here. So here we discuss how the reactants and products are related to each other thermodynamically and kinetically. Okay. So this is a potential energy on the y-axis, reaction progress. It can be any x-axis, like it can be of reactants, it can be of number of molecules involved, molecules involved. Okay, so this explain how the reaction process progress. The reactants always have, not always, reactant has lower energy than product. Wait, it is not exothermic reaction, it is wrongly written. So let me explain you an exothermic reaction. I have a reactant, it is a barrier, and this is the product. I will come on to this figure. First let me explain what is an exothermic reaction. This is a product, reactant, and this is the energy barrier, activation, energy barrier. So if the energy delta G, which I was talking about, Gibbs free energy, if P Gibbs of P is lesser than Gibbs of Gibbs energy of reactant, then it is an exothermic reaction. You are getting this much amount of extra energy, so it is an exothermic reaction. Products are forming, but also heat is also forming. Okay, what is a good example of this? If you have NaOH and water, then You get a solution plus heat because it is an exothermic reaction. Dissolution of NaOH particles in water is an exothermic reaction. Reversible, if it is reverse of this, reactant has lower energy and it is moving on to the higher energy that which has as products. So we have to impart some energy. You have to give some heat. You have to get some work done. That means it is an endothermic reaction. And in this, energy barrier become like more. Endothermic has more energy barrier than the exothermic. Right? Are you following this? Do you have any questions? We will be solving different questions in the next slide. Any doubts? Okay. I think nobody has any doubt over here. Then, what feature I was explaining over here, it is that, if this energy barrier becomes smaller and I term it as A and this energy barrier as B, which reaction will happen fast? A or B? The reaction with energy barrier A will be faster or reaction with energy barrier B will be faster? Which one will it be? If we think in terms of kinetics. A. A will be faster because barrier is less. But we can understand it in terms of distribution of energy. Let me tell you. Okay. My question is, why in case of exothermic reaction, or in case of these endothermic are at lower energy, right? And products are at higher energy. We know that every material wants to be stable. They want minimum energy. Then why this reaction is happening? Why they are able to cross that activation energy? They have this kind of energy, right? Reactant has this smaller energy. Then why they are willing to cross the activation energy? Because if we think overall particles, like if as in the lectures, if we have 100 particles, implying that we have 100 joule, does it imply that every one particle has 1 joule? Is it fair to understand like this? If a 100 particle box of 100 particles have 100 joule energy, then is it right to say that each particle has 1 joule energy? Is my statement right or wrong? Sanjoy, is my statement right or wrong? Yes. Why? Because Yeah, it depends upon. It depends on what? It depends on. It depends upon distribution of particles. Classical TD. TD means it depends upon distribution of particles. Yes, every some group of particles have different kind of energy. Suppose here I have 10 particles. This is the number of particles and this is the energy 20, 30. Then most of the particles have this energy. Around 25 particles have this on high energy, probable energy which we call. And they are very near to the activation barrier. A little amount of energy will give you product. And once product starts forming, it will disturb the equilibrium. And we know if we are going A to B to C, if we disturb the equilibrium on the product side, then the reaction will move forward. And we have disturbed the equilibrium over here. And that is why reactions start moving forward and we are able to get the product. And no laws of thermodynamics are are wrong. Like are all thermodynamic laws are valid. Stability of the material is valid. Okay, I hope you're following. So we are able to do this question on energy barrier diagram. Next part. Next question. If I want to increase the yield and accelerate this reaction which I is if the reaction is suppose A to B to C, and the reaction is look like this. It is an exothermic reaction. C A plus B. Okay. Yes. If I want to increase the yield and accelerate the reaction, this which has this energy diagram, then what should I do? Should I use catalyst to accelerate the reaction? Should I extract C from the reactor? Like if this happens in a reactor, should the option number 3 increase the temperature, or fourth extract C and use catalyst? Which one is the correct option? If I need both, increase the yield and accelerate the reaction, what should I do? Which option is correct? 3. Will the temperature will give you the yield? Suppose this reaction happens on 50 degree and you are saying that we have to increase the temperature. If I move on to 60 or 70 degree, will I get the yield or will I be able to accelerate the reaction? There will be no effect on yield. Yeah, there will be effect on acceleration. But I want to do both. Increase the yield and accelerate. Then which option is right? Which part of the reaction is depend upon the yield? What is your yield in this reaction? Is A is your yield or B is your yield or C is your yield? C. So which of the factor is affecting C? 2. Yani it means if we extract C, then we will get the yield. And if we want to accelerate the reaction, we need to what accelerate the reaction? Catalyst accelerates the reaction, not temperature. Temperature, yeah, no problem. It's okay. See, the reaction happens at 50 only. If you do give 60, 70, it is possible that we do not get product C. We will get a different product. We might get X product. We might get R product. Reaction is happening at 50 only. Lowering or decreasing temperature will change our product, but not give the reaction we want. So what we do, we will do two things. We will extract C, which why? Because C, removing the C from the reactor will disturb the equilibrium. One of the factor on the equilibrium depends is concentration. Concentration is less, then we will move. Then it always the concentration, always a gradient. Concentration gradient move from higher to lower. Okay. So here the concentration is low. To increase the concentration, it will move towards C to maintain the equilibrium. That is why extracting C. And what will happen if you use a catalyst? Catalyst function is to reduce the energy barrier. What happens generally if this is my usual exothermic plot? If we use a catalyst A plus B plus C, and if I introduce a catalyst, the energy barrier which was like this, now it is like this. Let me tell you. The energy barrier is now like this. The end product is same, but there is a decrease in the energy barrier, and instead of one energy barrier we have two smaller energy barriers. So it will be easier for the particles to cross two small barriers rather than the one large barrier. So usually this kind of energy change, the energy barrier happens in case of catalyst, and that is why more number of particles are able to participate and we are able to accelerate the reaction. Fine. Next question. So our option 4 is right. I hope this is clear. Next question. Which of the following is true regarding the activation energy? We have discussed much about activation energy. Activation energy depends upon the pressure of the system. The reaction rate decreases as the activation energy increases. Catalyst increase the activation energy of a reaction. Which of the statement is correct? Is it option A, B, C or D? Which statement is correct for the activation energy? Is this option is right? Catalyst increase the activation of energy, right or wrong? I just gave you the example. This third statement is correct? No. Because we know catalyst decrease the activation energy barrier. Yes, I will come to that option. Activation energy depends on the pressure of the system? No. Have we discussed any pressure related parameters over here? No. It is purely depend upon the energy it involves. Reaction rate decreases of the activation energy increases? Of course, yes. Because the barrier becomes higher and the speed becomes slow. So, option B, second only. Next question. Activation and this is a fill in the blank kind of MCQ. Activation energy of a reaction will dash the amount of products produced. What increase or decrease the activation energy will change or will not change the amount of product produced. Does think about like this. Does activation energy has any effect on the amount? If I have A plus B amount, like if I have 2 moles and if I have 4 moles, will there any energy? See the plot. How the plot will depend. Here is a reaction. Here is the energy. And here is a reaction coordinate. So does this activation barrier has any effect on the amount of products is produced? Right? No. The product can be produced faster or slower, but amount will remain same. If we have 2 moles, so it will give the same number of corresponding moles. It does not mean that we will get 5 moles out of 2 moles. No. So option 1 is right. Increasing the activation energy of a reaction will not change the amount of product produced. Not change. Consider the following reaction. X is in equilibrium with Y. The conversion of X to Y releases 5 kilojoule per mole of energy and has an activation energy of around it's 2.132 joule per mole. Then what is the activation energy of the reverse reaction? Is it option right? Third is right. We cannot be determined from the given information. Reversible reaction. It is a reversible reaction, right? So is third option correct or not? So we will solve this numerical. X to Y give 5 kilojoule. The activation energy, so Y has 5 kilojoule mole energy. Okay. The activation energy from going Y to X is 2.32. Okay, sorry. Wait, I will write it. 2.32 joule. If we convert joule into kilojoule, then I have 2.32 kilojoule per mole. And I want to go back to X. Then the correct answer is 7, around 7. 5 plus 2, 7.32 kilojoule per mole. So option 2 is right. Okay. Option 3 is incorrect. We have enough information to determine these values. I hope this numerical is clear to you. Next question. This is a chart in which on y-axis I have enthalpy of formation, relative enthalpy of formation. I should write relative enthalpy of formation and the different carbon allotropes. Different everything is a have carbon atoms but with different structure and different properties. So tell me from this chart Which is more stable, graphite or C60 fullerene? Which is more stable by seeing the energy values of this chart? Graphite. Can you read this chart? The graphite lies over here. The relative energy is 0 kilojoule per mole. And where C60 lies? C60 lies over here. It has around 40 kilojoule per mole energy. So which is more stable? Graphite. Okay. So there are various things in this. So this Di means diamond. Okay. Z means it is a uh, uh, carbon nanotubes. In last class I gave you the example of carbon nanotubes. They are cylindrical 1D structures, nanostructures. So Z means zigzag. Zigzag carbon nanotubes. They are different like different orientation. A stands for A stands for arm chair carbon nanotubes. CNT carbon nanotubes. Okay, and the whatever number is written in the bracket, it means that much number of carbon atoms are there approximately. Okay, 1.4, 1.2, C8, C180, C140, C120. Okay, so here this is the explanation of the chart. Coming on to the next question. Why fullerenes are thermodynamically stable at, as you can see in this chart, here I have C60 fullerenes with higher carbon atom, and here are others like 120, 140, 180. The energy is become lower. Energy is decreasing. Why? Why with increased number of carbon atoms, the thermodynamic stability of the fullerene is increasing? Any answer you have? Should it happen or not? Is the what the statement is, first tell me, is statement correct or incorrect? Statement is correct, but it is happening so because the more number of atoms, more number of carbon atoms are introduced into the structure is losing its stress. Okay, it is very constrained. So when you increase the number of carbon atoms, the structure kinds of open itself. It has more space. So that is why it has become more stable. It loses stress, it loses the energy, it becomes more stable. That is why enthalpy is decreasing. From the graph, tell me what is the enthalpy of formation for C240 carbon. This is C240. What is the enthalpy from the chart? Tell me. Yes, around 18. And what is of diamond? Approximately. Yeah, 3, 2 we can say. Okay, I hope this question is clear. Now moving on to next question. Conceptual problems on specific heat. What is specific heat first? What do you mean by specific heat? Specific heat means amount of heat energy required to raise the temperature of 1 gram of material to 1 by 1 degree Celsius. If I have 1 gram of material and I want to increase the energy by 1 degree, that energy required or heat required is called specific heat capacity. So the problem based on this is, what is the specific heat capacity? Okay, so let me tell you the equation first. C is my heat capacity, Q is the heat required, M is the mass, and delta T, the temperature difference. Suppose the material was already on 25 degrees Celsius and I want to take it to 50, around 40 degrees Celsius, then the delta T will be 15. Okay. So question is, what is the specific heat capacity for the 50 gram sample of metal that increases in temperature by 10 degrees Celsius when 2000 joule of energy is added? And tell me, after solving the question, tell me the units of specific heat capacity. So 2000 joule into 50 gram, everything should be in SI units. 50 gram changing into the kilogram, and then 10 is what is the correct answer? Units. Okay, right. It is joule per kilogram degree Celsius. We may not need to convert into the kilogram. Yeah, we need to. We need to convert into standard units, right? Next question. A 2.5 gram sample of an unknown metal at 100 degrees Celsius immersed in water and is allowed to reach equilibrium if the final temperature of the system is this 25.1 degrees Celsius and 84 joule of the energy are released. You have everything. You have to find a specific heat capacity and then tell me from that capacity matches with which of the metal. So I have 84 joule. I have 2.5 gram to 10 raised to minus 3 into 100 minus 25.1 degrees Celsius. What is the answer? Answer will be related to iron. Okay. I have other slides to cover. Next question. Next, coming on to the next part of the problem. Phase. What is a phase? I have told you multiple phases, single phase, the single crystal. Hmm. By phase, it means it is a homogeneous physical matter like liquid, gas. Okay, these are phases. Okay, that is a phase. Solid solution is a phase. Okay, it is not, equilibrium is a condition, but phase is a physical matter. So this is the definition of phase. So understanding phase, we will understand phase by other things also, like next question. A phase diagram shows the relationship between phase. What is a phase? Let me tell you. Here I have temperature. Somewhere here is volume. Like if I have two phase, copper and nickel, 0 to 100. This is 50. And some composition is forming over here. Wait. Let me explain you again. This is copper. This is nickel. This is temperature. And one single phase has been formed like this. This is a phase diagram of copper nickel. 0, 100, and this is 50. Then this explains how copper and nickel reacts with change in temperature. Here phases are forming. So below that it might be solid. It is solid, not might, it is solid. Below this temperature, both are in solid form. Above that phase is liquid form. And here reaction is happening. So here we have solid solution. So the answer of this question is phase diagram shows a relationship between temperature and volume and three phases of matter. Okay, this is a binary solution, so we do not have all phases of matter every time, but three phases of matter are there, like 1, 2, 3. Solid solution is also a phase, right? So three phases are there, so this option is right. On a phase diagram, the intersection of solid, liquid and gaseous line is known as critical point or triple point. This will give you the definition. What is a triple point? Triple point. On a phase diagram, the intersection of solid, if I have some phase diagram like of water, we have something like this. Here is solid, here it is liquid, here it is gas. This point, this is temperature, this is this point, here it's pressure or sometimes. This point is called triple point. Okay. And this ends with our today's lecture. Do you have any doubt? Any slides you have doubt with? I'm reversing the slides. Okay. So in next class we will discuss the assignment. The last date of assignment is 9th August, and we will discuss the next two assignment of week 1 and assignment of week 2 and other summary lectures of week 3. Okay. Thank you class. You're welcome, Sanjoy.